Okay, for the next subtopic, we are combining two subtopics, 17.2 and 17.4. Both of them are about standing waves. Okay, let's take a look at the figure here. The figure is showing multi-flash photograph of a standing wave on a string. As we can see here in the graph, we can see label of antinode here. This one antinode, this one is node. So what can we define with antinode and node? We can say that antinode is the point where the maximum amplitude is, and the node is the point where amplitude is 0. So I just write down here maximum amplitude, and this one is 0 amplitude. It is actually the point where the amplitude is maximum is called antinode. The point where the amplitude is 0 is called node. Okay, together with this one, we have the wave function. According to this standing wave. So the wave function that we are going to apply later, inshallah, is y equals to 2a sine kx cosine omega t. So this is the wave function of a standing wave. Wave function of a standing wave. Okay, next. Let's take a look on these figures. Actually, we have 3 figures here, A, B, and C. What is actually happened here? Actually, we have in figure A, we have two traveling waves. They are traveling towards each other, and as we can see here, y1 and y2, the two waves are in phase. Because of these two waves are in phase, the resultant wave will be constructive interference, and it will experiencing a maximum displacement from the equilibrium. So the third one here will be the resultant waves. So combine y1 plus y2, y1 combined with y2. Then we have the amplitude is increasing, where the maximum amplitude is labeled by A, antinode, and the one with the point of 0 amplitude is labeled by node and antinode. Okay, in figure 2, the time from 0, now 1 quarter after that, 1 quarter period later, the traveling wave move 1/4 of wavelength, and now y1 and y2 are out of phase. They are out of phase, and therefore it will result zero displacement here. So this is also the same, combining y1 and y2, and because they are out of phase, then the resultant will be 0. Okay, next, in figure C, at t, now move further to 1/2 of the period, the traveling waves y1 and y2 again are in phase to each other, and we are having the same what we have in figure A. They are in phase, and the amplitude is increasing after it is combining y1 and y2 here. Okay, right. So that is about the standing wave, the node, and the antinode. Now, let's take a look the details on the standing wave together with the node and antinode. and also another equations. Let us consider a string. Okay, this is a string. This figure number 1 here. The string with a length of L is connected and fixed at both ends. They are fixed at both ends from the wall to another wall. Okay, next one, we are going to have vibration. We give the vibration to the string, and let's take a look the second one, which is figure 17.14a. Okay, stated here the normal modes of vibration of the string in figure 17.3 from a form a harmonic series. Okay, form a harmonic series. What is harmonic series? So harmonic series means this is N1, N2, and N3. So this is called the first harmonic or fundamental. Okay, and the second one is called second harmonic. The third one is called third harmonic, and so on and so forth. If we have fourth harmonic, we can have fifth harmonic. We can go higher and higher and higher. Okay, all right. Let's go back here to our from figure 17.13, 17.13. It vibrates at the first harmonic. So for the first harmonic here, there will be two notes. Okay, two notes produced at both ends of the fixed string, and we have antinote, one antinote. So from here, this is called the fundamental of first harmonic. So this N is also known as number of segment. Number of segment. N. So for the first harmonic, we have one number of segment. For the second harmonic, we have N equals to 2 segments. And for the third harmonic, we have 3 segments. So what is the meaning of segment? Okay, this is the segment. Segment. Okay, one segment. Okay, this is 2 segment. 1 and 2. 3 segment. 1, 2, and 3. 3 segments. Okay. Okay, according to the first figure here, the string with a length of L. So the length of the string is fixed. The length of the string is not changing. Okay, it is fixed. What changes here is the number of segments when the string is vibrating. So as we can see for the fundamental or for the first harmonic, if you notice that we have this equation here, L equals to 1 over 2 lambda 1. Okay, L equals to, for N equals to 1, we have L equals to 1 over 2 lambda 1. Okay, again, what is lambda? I hope that you still remember what is lambda. Lambda is a wavelength. And how to know the length here equals to half lambda? Okay, please, let's take a look at the second segment. Okay, this actually, before I forgot, number of segment is referring to N. Referring to N. Okay. And for second number of segment, we have, or second harmonic, we have number of segment equals to 2, and the length equals to lambda 2. Lambda 2. Okay, right. For the first segment, we have one number of segment, and L, the length, equals to 1 over 2 lambda 1. Okay, let's take a look for the third one. The third one, again here. Okay, number of segment equals to 3. So 3 number of segment. L, the length, is equals to 3 over 2 lambda 3. Okay, length is changes in terms of lambda, wavelength, okay, in terms of lambda only. So we have if we have 4 number of segments, then we have n equals to 4, n equals to 5, and so on. We can have more than that. Okay, let's take a look. How to know it is lambda 1, lambda 2, lambda 3. Okay, let's have this one. I think I have to maybe sketch here in the next page. Okay, let's take a look on this sine curve. Okay, this is let's say the string just now. The string with a length of L. Okay, so I'm going to sketch the sine graph. The sine graph 1, 2, 3, 1, 2, 3, 4. Okay, and now let's say this one here, and then over there. Okay, it is not perfect, but we have a shape over there. Okay, in this shape, we know that from previous one, we know that the node is the point where the amplitude is 0. So this is node n. So we label this one with n. This is n, and this is n. And we have antinode at the point where the amplitude is maximum, or displacement is maximum. We have A here. Okay, this is what we call that the sine graph, and with the length of L. So with length of L here, the length is not changing, but okay, from here we know that this is equals to 2 pi radian, pi over 2, and this is 3 over 2 pi. Okay. Alright, what is actually lambda? Okay, lambda is measured from either crest to crest or from trough to trough. And from here, yes, it looks like we cannot simply measure the lambda from crest to crest or from trough to trough. So let's have another curve here. For example, we have another curve. Okay, so this time we are going to focus on the lambda. Okay, let's say we have this one, and we have to have again sine graph with at least 2 crests. So we have this one. So it is not perfect, but we can see the shape. Yes, okay. Right. So again, we have the label already here. Remember the label N A N A N. So again, we have maybe I need to have the label here. N. This is N. Sorry. This is N. This is N, and another N that over there. Okay. So now we can simply have or we can simply label the lambda here. This is lambda. Oh, sorry, from crest to crest, which is equals to lambda. Okay, this is lambda. Okay, now from crest to crest, so we have here, actually we have antinode here. This is, oh sorry, again, this is antinode. This is antinode down there. This is antinode here. Okay, so from here, actually we can measure the lambda. We can measure the lambda. As we can see, I'm going back to the previous page. As we can see here, the distance of L. Okay, L is now going to be now for the first segment. Okay, we focus on the first segment first here. The distance. Now the distance is from node to adjacent node. Okay, this is node to adjacent node. For the second segment also we have from node to node, but it is not adjacent node. Again, same goes for three segments. The distance from wall to wall, or from x equals to 0 here on this figure 17.13 to x equals to L. It is also from node to node. Okay, it is actually impossible for the fixed end of the string to have antinode at the end, because yes, it is impossible. It cannot have antinode at the end of the fixed string. Okay, now we are going to measure the lambda, okay, in terms of L. Okay, now the first segment here, or fundamental, or the first harmonic, L is now having a distance from node to another adjacent node. So, okay, let's take a look what we have here. Okay, now let me have this one. Okay, now we have lambda is from antinode to antinode. Okay, to make it easy for us to measure the distance from node to node. Okay, L is now, okay, again go back to the previous page. In our case here, we can say that the L here is equals to the distance from node to node. The distance from node to node. Okay, this one is actually adjacent node. Adjacent node. Okay, distance from adjacent nodes, from node to node. Kalau let's say for n equals to 2, the distance from adjacent node to node is from this wall to this node. So meaning that here, simply we can say 1 over 2 lambda plus 1 over 2 lambda will equals to L. Okay, that is what I'm going to show you. Okay, so this one we have, let's split this one. Okay, we have node, antinode, node, this one again antinode, this one node, this one antinode, and this one node. Okay, so we can say that, okay, let's focus on, let's say we focus on this one, on the lambda. Okay, lambda is here. How many segments do we have? 1 segment, 2, 3, and 4. 4 segments. Okay, we have 4 segments over there. Okay, so lambda divided by 4 will be actually equals to, let's say lambda over 4 equals to the distance from node to antinode. So this is from node to antinode, and again from antinode to node, from antinode to node, and from node to antinode. Okay, and also will be equals to distance from antinode to node is the same. So we are now defining or saying that this is the distance from node to adjacent antinode. Yang sebelah dia, from node to antinode, or from antinode to node. So meaning that here the distance from node to antinode is equals to lambda over 4. Okay, from lambda over 4. Meaning that here we can say that figure sebelah dia, the figure sebelah ni lah, I mean So let's say we divide this one also. Okay, kita pun divide node. Sorry, this one node, this one anti-node, this one is node, this one anti-node, and this one is node. So if we combine this with 1 over 4 lambda, this one 1 over 4 lambda, this one 1 over 4 lambda, and this one is 1 over 4 lambda also. So we can say that L, okay, this is this L, the original the original figure before having vibration. So L here in terms of lambda will be, this one is adjacent from node to node. So meaning that if we divide this one, it will be 1 over 4 lambda, 1 over 4 lambda. So it will brings us, or resulting to have 1 over 2 lambda. Okay, so same goes for the other harmonics, second harmonics. So we know that the first harmonic, that the length of L equivalent to 1 over 2 lambda 1. So we have here, as I said just now, 1 over 2 plus 1 over 2 will be equals to 1, equals to lambda. Okay, same goes to this one. We have 1 over 2, 1 over 2, 1 over 2, or 1 over 2, 1 over 2, 1 over 2. Oops, sorry, it's not 1 over 4, it is 1 over 2. So we have 3 over 2 lambda 3. Why lambda 3? Because it is third harmonic. This is lambda 2 because it is second harmonic. This is lambda 1 because it is the first harmonic. Okay, and then from here we can have the equation. Actually, we can have equation. Actually, one more thing is this is for first harmonic we have 1 loop. Second harmonic we have 2 loops, and third harmonic we have 3 loops. Meaning that the more the loops, the higher the frequency. Okay, then from here we can have the equations for higher frequency. Okay, if we are going to apply the calculation here for higher frequency, or generally we have the equation of Fn equals to Nf1 equals to N over 2L times T over mu, and N can be 1, 2, 3, ... Okay, this one, for example, we have, let's say we are going to find F5, frequency for the fifth harmonic. Frequency for the fifth harmonic, F5 will be equals to 5 times F1. So 5 times the fundamental. We will get the answer over there. Okay, same goes to let's say we have we are going to calculate second harmonic. Second harmonic, we have F2 will be equals to 2F1. So the fundamental or the first harmonic is very important here and everywhere. Okay, right? So this equation is actually coming from okay, where this equation is coming from. Okay, now let's take a look at this one. We have wave speed. Okay, let's say we have wave speed. Now I'm going to delete this one. Wave speed, from the wave speed ataupun from speed of wave, kita ada V equals to F lambda. Okay, V equals to F lambda. Let's say we're going to find F. Now F frequency, and now fundamental. Okay, fundamental frequency, we have F1 will be equals to V over lambda 1. Okay, what is lambda 1? What is lambda 1? Okay, lambda 1. We know that L equals to, for the fundamental, L equals to 1 over 2 lambda 1. Okay, so from here, lambda 1 equals to 2L. Okay, lambda 1 equals to 2L. So we are going to substitute this into our equation in the next page, which is V over 2L. Okay, right. So what is V? We already introduced. We already found in the previous chapter. We have square root t over mu. So we are going to substitute this square root t over mu. So this one I just write down here. V is sec t over mu. So we are substituting this one. We have F1 equals to 1 over 2L square root of t over mu. So this one is the fundamental. So for a higher frequency, that's we are going to here, which is any frequency can be equals to F1, the fundamental, times the number of segment or number of frequency that we are going to find. And then we got this equation. If we substitute here, F1, it will be F1 equals to this equation. Go back to here. Okay, alright. So, okay, that's it for this subtopic.